Okay.
So maybe we can start. So welcome everybody. We are here for the habilitation à diriger des recherches of Francesco Bronzino. So Francesco, you have 45 minutes of presentation and then we will switch to the question session.
Okay. So let me just move these so that it's easier for me to see. Okay, today we're going to talk about the work that I've been carrying on for the last about 8 years. That coincidentally started exactly in the moment I moved to France for my postdoc at Nigeria. And that has been focusing for the most part on trying to make it easier for people to take advantage of new technologies like machine learning and artificial intelligence in deploying networked systems. So, clicker doesn't work. Works now, awesome. So, machine learning and more broadly artificial intelligence are everywhere these days. I'm sure that all of you have seen at least one of these articles that claim that artificial intelligence will revolutionize the way most of our activities work. In the image here, I'm showing you an example of these apply to the context of human resources, but I could list an infinity of examples going from business to healthcare, and even countries as a whole are investing a lot of their resources into this AI dream of sorts. And networking is clearly not an exception of this trend. Why is networking, why is machine learning attractive to networking people? Well, first and foremost, networking problems are very complex. Networks are accessed by a number of different devices these days. They go from laptops to mobile phones to autonomous systems like robots and cars. And all these machines connect to a large variety of services. To make things worse, networks are large and complex ecosystems made of very different protocols and languages, where packets are exchanged at always increasing speeds. And if this was not enough, well, everything is becoming encrypted these days, meaning that network operators that want to understand what's happening in their networks don't have visibility anymore into the traffic that is traversing their network. On the other hand, machine learning is very tempting as a technology. Because it helps solving complex problems like the networking ones, and at the same time has become kind of like a commoditized technology, meaning that it has become very easy these days to take an existing data set, throw it into one of the many tools, like some of the ones that I'm showing here in this slide, and try to train a model that is then going to achieve a given performance that, if we're good enough, it's going to be good enough to help us solve a given issue. And obviously, this trend has been rather present in the research networking community. And in fact, we can see many examples. Security people were some of the first ones to adopt machine learning to solve challenging problems, such as detecting attacks onto their networks, detecting malware injection, so on and so forth. And then we're seeing these type of technologies expanding to different types of problems across the networking space, like classifying the traffic that is traversing our networks, inferring the quality of applications that are being transmitted over the network, or even learning how to route, learning the basic tasks that networking people need to be able to perform. This trend is not stopping, and now we're seeing people trying to take advantage of the newest generations of AI techniques like large language models to solve problems that are still open in this space. And yet, if we talk to operators, in particular, even more when we started this whole line of work, in practice, not so many people are really using machine learning or AI and deploy it into the operational networks that they have to manage. And there are a variety of reasons, and I'm going to try to explain you some of the ones that we've been tackling on. And we're going to do so by looking at the standard pipeline that is commonly used for training machine learning models. This pipeline could be transported, at least for the gray boxes, to pretty much any domain. This pipeline goes from data collection, that in the case of networking consists of taking some traffic from the network, either by raw registration of traffic traces, or using some measurement systems like NetFlow, SNMP tools, and so on. We're going to do some steps to clean up this data and prepare it through feature engineering to be given as input to the models that we want to train. Once we have our data ready, we're going to train some models, test them, and if we did a good enough job, we're going to deploy it, or we're going to circle back and start again if we need to collect more data and so on. So what are the issues? The issues actually can manifest themselves at different steps of this pipeline, but let's focus on one specific example for the context of this talk. So let's focus on feature engineering. What does it mean performing feature engineering or creating some data representations of network traffic? So let's start from the beginning. We have our network. We have a couple of routers, the machines that are exchanging packets. We are going to collect these packets and apply some transformations to the data that we are collecting. These transformations can be of different kinds, different types of operation, mostly like some mathematical application on top of them. To give you some examples, some of the transformations that we can apply are aggregation and sampling, meaning that from our traffic, we're going to capture how many flows, so the end-to-end exchanges between applications are happening in our network, how much throughput our applications are generating, how many packets are being lost, so on and so forth. These are the typical operations that network operators have been applying to their networks for the longest time. Other types of transformation might be applied to trying to detect specific events that are occurring in the network. For example, the establishment of a connection between a client and a server, or a client sending a DNS request to translate a URL into an IP address, so on and so forth. These also are fairly common. And then there are new representations that researchers and alike are always trying to explore. An example here, this QR code that I'm showing is intended to represent some new attempt at providing representations in the form of images for network traffic. Why doing so? Because some researchers noticed that AI and machine learning was particularly effective when applied on images. So they asked themselves, how are we going to transform packets into images and then make them go through our machine learning models? And normally this can be done with, like, for example, a gray scale image like the one shown here. So now we have established what it means to create representations of the traffic. Let's look at what problems might actually arise when applying these representations. Let's say here that we want to model a problem, and we're going to use different groups of representations as training and input to our models for solve this issue. What specific inference problem we're solving here, it's not that important. But what's more important is the groups of representations, traffic representations that we're using. So first, the one on the left, the circle, that's one group of representations that we're going to call network representations, that when used for training is going to produce an accuracy of our model that is going to be about 72%, let's say. If we add another traffic representation to our model, we're going to call it application for the sake of this example, our model performance is going to improve, and we're going to get the triangle model here that is going to get somewhere around like 83% of accuracy. Then we're going to add one last set of representations, and now we have like 3 representations, so we're going to call them all, and we're going to get the diamond model. And the diamond is going to still one step further improve our model performance to about 84%. So if I'd shown you this figure and I ask you what model you'd like to use for the inference problem we are trying to tackle, most likely you're going to say, I'm going to take my model on the top right because highest accuracy means best performance when we deploy the model. Now let's take this example one step further and let's look what happens when I give you one more piece of information and one more dimension to this plot. And in this case, I'm showing on the x-axis the amount of state, so the amount of memory that it takes for a measurement system to collect the data that we are going to need to use to perform the transformations and give them as input to our models. So we can observe here is that, sure, technically our diamond model is still the best performing one, but now we can observe that to collect the information that that model needs for executing, we are increasing the cost of memory by 2 orders of magnitude. The takeaway from this figure is that, sure, it is true that the diamond model is the best performing, is the most accurate one, but what is the cost of this increased accuracy? And this problem, this example, falls into the broad concept of what is commonly known as the hidden technical debt in machine learning systems, where the technical debt is those inherent costs, inherent complexities that arise when we want to apply machine learning to systems. And problems such as the state costs that I've shown you here are some examples, and other challenges might arise. This paper that I'm showing you was presented by some Google researchers in the context of the software engineering domain. I'm going to try today to give you some examples of the type of technical debts that arise when applying machine learning to the context of networking systems. And I'm going to do so obviously in the context of my research that is intended exactly to achieve solve the problem of tackling the challenges that arise when we try to make network systems work in the age of machine learning, meaning that we want to use machine learning to make our systems work better, be more effective, but we have to solve the inherent challenges that comes from these applications. So my research took various directions, tried to tackle problems that arise at different moments of the machine learning pipeline that I've shown you before, in particular going from problems connected to the scarcity of data, the need for data to train our models such that they're going to perform effectively, the problem of designing models that can work effectively when deployed into the networks they have to live, they have to be performing in, similar to the example I've just given you. And then the problems will arise when we want to deploy these models for a long amount of time and make them work as the network conditions evolve. There are different contributions that are part of this manuscript and that are spanning these 3 macro research directions. And on top of that, there is a 5th one that was kind of like the motivating work that inspired a lot of contributions that came after, and that focuses on one of the core use cases for machine learning applications in the network, something that I started working when I moved to France, as I said, which is the inference of video quality from encrypted traffic. For the sake of time, I don't have time to cover all contributions in this talk, so I'm going to focus on 3 main contributions next. And I'm going to start from the use case, the problem that kind of initiated this line of work that I've been spending so much of my time on. The inference of the quality of video streaming applications that we all use, like YouTube and Netflix, by solely looking at the encrypted traffic traversing our networks. So first off, let me convince you on why this problem is important. Video streaming represents a bit more than 70% of the entire traffic that is traversing today's networks, meaning that it's by far the leading application generating traffic in our networks. This trend is not slowing down anytime soon, and is actually possibly increasing due to new forms of media popping out every day, like, for example, virtual reality that requires even more data to be transmitted to achieve to be streamed to the users. So due to the importance of these applications, operators historically wanted to make sure that this video was well delivered to their users, and so apply different optimizations techniques to achieve best possible quality for the users of their network so that they will not complain. Some of these techniques span from changes the video that traverses their network on the fly, or more simply applying some rerouting, some traffic engineering to compensate for performance decay and make the packets of these services traverse better path and improve the quality of the applications. As I said before, this has become very challenging and almost impossible to perform given that network traffic is now encrypted and operators don't have any more visibility on what's traversing the network, and so they have a much harder time applying any of these techniques, even the simpler ones like rerouting. So at the beginning of this project, we started tackling this challenge, provide a new visibility into the application performance for network operators, and we started by applying our machine learning pipeline that I'm giving you here in a more visual form. So we started collecting some traffic that belonged to network operators. We wanted to create our data set as input to use as input to our models. We grouped the net traffic representations that we selected as candidates for the models we want to deploy into three macro groups: network layer features, which are the features that can be easily collected by simply looking at the network layer of the packets that are traversing the network; transport layer features that require tracking the state of the transport protocol that is used for exchanging messages between the endpoints of the communication, so our video clients and video servers. And finally, the application layer that is not any application of deep packet inspection to look into the application content itself. That's encrypted. We already said that. But it's more some techniques that look at the patterns of traffic over time in order to isolate specific behaviors of the application that can help with the inference problem. In this specific case for video, we were capable of isolating the downloads that occur for transferring smaller portions, so segments of 2 seconds of video that are downloaded over time by video clients for the specific protocols that are used in today's streaming applications. So something that characterizes these features is that they're relatively easy to collect, but require some specific implementation. We use this data to then infer different quality metrics, like how long it takes to start the video, the startup delay, or what is the resolution of the video that is being streamed. I'm going to focus a little bit more about resolution today. So we wanted to collect this data. I started as a postdoc to implement a lot of tools to collect this data. We implemented some Chrome extensions, some browser extensions to extract the video quality, the ground truth of the applications that we wanted to track. We were focusing on 4 main video streaming services like YouTube, Netflix, Prime Video, and Twitch. And we deployed a number of clients that will automatically stream all day long different videos from these platforms. And we also implemented some form of emulating different network conditions in order to collect a very diverse data set representing a variety of network conditions. By doing this, we collected more than 13,000 video sessions of about 5 to 8 minutes. We grouped all the statistics into 10 seconds intervals where we computed the representations that I've shown in the previous slide for every 10 seconds. And we started training various models to see which one would be more effective. I'm going to skip the part, all the models that we tested. I'm going to stick to the fact that random forest for our specific application was the model that worked best. We started analyzing, in particular, the effectiveness of the different models when using different groups of traffic representations. And in particular, the combinations of the 3 macro groups that I've shown before. Here I'm showing a precision and recall plot for the performance of the 4 models for inferring the resolution at 10 seconds intervals, as said, of different groups. So the blue line is the performance only using network features. The orange line is network plus transport. The green line is network plus application features, and the red one is the one using all features. You probably are starting to reconnect with the examples I've given you before. What are the takeaways from this plot? First of all, you must know, if you're not familiar with precision recall, that best performance will imply a line that passes along the top right corner of this plot. So what are the takeaways? The first one is that, for obvious reasons, the blue line is the one performing the worst. That's because network features are limited in the information that they can provide to the models. The second line, the orange one, improves this performance, but surprisingly, at least for us, the transport features were not really providing that much information that could help improve the model. In contrast to the green line and the red one, that both employ application layer features. To an extent, this was expected, because if you collect application behavior, your model is going to improve performance. At the same time, it was surprising because we expected the orange one to help quite a bit. So this was a very good result for us, because we were able to improve performance and achieve very good performance, but performing data reduction, because we demonstrated that using transport features that can be hard and complex to collect inside the network, because you have to track the TCP state of every single flow that you want to track, were not necessary to achieve optimal performance. This was a very good result, and we exploited it to deploy these models that we developed on a large-scale deployment. We deployed a system to collect traffic traversing the network connections of about 60 homes spread across the US and France, in particular Paris in France. And we collected about the traffic statistics for more than 210,000 videos for a period of 16 months. This deployment was performed with the goal of exploring the relationships that exist between home network speeds that people buy from their operators, and the quality of the videos that they will get for their money. Sadly, I don't have time to explore these results in this talk due to time. The main takeaway that you can take home with you is that speeds have very little influence on quality after a certain relatively low threshold. But what were the important takeaways of the study from the model's perspective? The first one was that we were capable of achieving state-of-the-art performance, improving over existing models, but also reducing the amount of data that was necessary to execute these models, making our model more practical, because it was much easier to deploy them in different conditions. And in fact, the fact that we were capable of deploying them into the homes of a large collection of houses demonstrated that these models were practical, that anyone could take these models and deploy them in practice. At the same time, we were aware that many limitations still existed for these models. Mainly, we identified 3 limitations. The first one was that the data set that we collected, that we used as input to train these models, was solely collected from a lab environment, meaning that for as much as we put effort in emulating different conditions, we will have never been able to fully replicate the conditions that we would have then experienced in a real deployment later in time. The second limitation was that it is true that we were happy that we were achieving this data reduction, and we kind of had set the goal of not using TCP information in the first place. But the only confirmation of the deployability of these models was the fact that we had indeed been able to deploy them, but we had no sense of whether these takeaways could transfer to other type of deployment scenarios. In other words, we were not able to quantify the benefits of the data reduction that we were achieving. And the last limitation was that we had captured our training data from a specific snapshot in time, meaning that if any change in the services that we were tracking and happened during the duration of our study, we would not have been able to capture it with the models that we had developed. So the rest of today's talk focuses on how we solved and attacked the two latter limitations that I identified. And I'm going to start from the first one. In particular, how we developed a system and a technique to evaluate not only the performance of the models in terms of accuracy, but also in terms of the cost that they incur in the measurement systems that they are deployed on. So I just talked about the video use case and how we were able to to achieve state-of-the-art performance with that reduction. But the only reason we were capable of doing that is because we had started working with raw data, so traffic traces, PCAPs, commonly known as PCAPs, and we had explored by creating new representations that might be the most effective. So in practice, if we had stuck to what normal measurement systems would have given us, we would only been able to achieve the blue line. That's what a normal measurement system like NetFlow will have provided us. But then with our explorations, we were capable of pushing the performance towards the top right corner, in particular developing our application representations. But the compromise was that this was achievable only by collecting this data in raw format, like collecting it in a control laboratory and being able to explore it. Obviously, this does not scale with the vast majority of environments, and what the plot on the right shows you is the amount of data that would be required to collect PCAPs at line rate when applied to a 10 gigabit link. Basically, just in a few seconds, we're going to make our link explode, and it's impossible to apply the same types of exploration that we achieved. So the question that we ask ourselves is like, how can we be able to develop a system that enables us to basically explore the blue area of this very simple Venn graph that merges the models that achieve high performance, meet the accuracy requirements that we want to target, but also that satisfy systems constraints when deployed in practice. And this is where we design Traffic Refinery as a solution of this problem. So Traffic Refinery is a system that creates the representations that we talked about before and is tailored to achieving the goal of maximizing model performance and systems constraints. It does so by developing three main modules, three main design choices, and I'm going to explore them in detail right after. The first one is that Traffic Refinery makes it very simple for people to collect traffic from the network, either in a control laboratory or in deployment because it supports high speed. But it also makes it very simple for users to explore the features that might matter to them. In particular, it makes it very simple to implement new features with just a few lines of code and deploy them rapidly and iterate to see the impact that they could have on the model performance. On the other hand, it does so by enabling up to 10 gigabit per second capture support, and also profiling as a built-in feature the various systems costs that might arise with the collection of the features and representations that are being captured. In particular, we focus on three systems costs: the amount of state, so the amount of memory necessary, the amount of processing in terms of CPU cycles and time to process packets, and the amount of storage, so the amount of data that has to be exported from the system. All these was intended to provide a concrete quantification of the system's cost that one will incur. And something interesting about this system is that it could both be executed on pcaps collected from any environment, so imitating any collection vantage point possible, or deployed in actual networks. So thanks to this system, we learn a few takeaways from two use cases. Here, because we focus on the video quality inference use case, I'm going to focus on the takeaways that we learned from that one. So first of all, we only needed about 100 lines of code to extend Traffic Refinery and implement all the representations that I've shown you in the previous slide, meaning that this was already a quantification of how easy it would be for a user of this system to deploy a complex use case like the video inference one in a real network. The second and very interesting takeaway is fundamentally the figure that I've shown you at the beginning of this talk, where we were able to quantify for the three representations that I've shown in the example, what will be the actual concrete cost of collecting the diamond, as I called, model at the beginning of the talk. Now you know that these basically all the groups of representations possible, and compare these costs with respect to other models, in particular the one with the data reduction that we had achieved, the one using only network and application features. So, as I said at the beginning of this talk, we were able to demonstrate that transport features are orders of magnitude more costly to collect. Interestingly, though, we were also able to demonstrate that this is true for state costs, for the amount of memory, but is not true when considering processing time. So here I'm showing the average per packet processing time, so how long it takes to process one packet for all of this representation in average over time, and this is like a cumulative distribution. So while it is true that the rightmost line, the orange one, is still the transport feature, so they're more costly to collect, if I put this plot into perspective, you're going to notice that for a system like Traffic Refinery that collects traffic at 10 gigabit per second, the average per packet time necessary to collect all these representations is well within the limits necessary for being able to sustain a full link of data collected from the network. So this was the first contributions that I focused on. The second one looks at the problem of model performance over time. Let me show you through an example what problem we are looking at tackling, and what problem we're looking at tackling. So let's assume that we want to, as network engineers and network operators, we want to create a forecasting model for predicting what is going to be the traffic demand, say for video services, like we said before, in the future based solely on information that we collected from the past. This is the typical forecasting problem that network operators want to put in place to be able to quantify the amount of the demand that they are going to experience in the future. So what will a person developing this machine learning model do? Well, first it's going to collect some actual data over time, representing the demand oscillating over time. It's going to use this demand as training data for the model. And it's going to use the produced models to predict the demand in the future. If the machine learning model designer will have done a good enough work, the model is going to provide the predictions provided by the model are going to resemble close enough the actual data that later is measured from the network. Over time, we're going to continue using our model and make predictions about the future. But let's say that at some point, a new algorithm is deployed in these video streaming services, or in the case of the network, a new service deal is cut with another operator, changing the way the traffic traverses our network. And we might end up with something resulting like this, where our model predictions are very distant from the actual performance that the network, the actual demand that the network experienced. This is what we commonly call concept drift, which relates to the divergence of the data distributions that we are using as input and the corresponding outputs that the model is giving us. So we wanted to work on concept drift. Concept drift is kind of like a known entity in the networking space, with the catch that it's very hard to study concept drift in this space, because the only way you can do so is by looking at very longitudinally data sets that span a long amount of time. We were lucky enough, though, to collaborate with a network operator that provided us a data set that corresponded to this characteristic. And in particular, we were collaborating with an operator in the US that provided us a data set spanning about 4 years, from 2018 to 2022, and consisting of a variety, 224 to be precise, key performance indicators collected from the base stations, so the elements transmitting data in the network, in the cellular network, KPIs representing different types of information from resource utilization, network performance, and user experience, and doing so for an entire metropolitan area. So an area consisting of hundreds of base stations. In total, in the dataset, we had almost 900 base stations present. 412 of them were present all along, already showing how much a network can evolve over time. Basically, in 4 years, there were almost twice as many base stations as we had seen from the beginning. And for each day, we will collect a log of all these KPIs for every single base station present in the dataset. So the first step that we took was actually, validating that concept drift is actually a problem in the context of networking. So here I'm showing you a model that we trained to forecast the demand, so the amount of downlink volume that we will get in the network in the future using 90 days of training data. So we took the first 90 days of the data set, we trained a CatBoost model, and we use it to forecast daily measures of downlink volume over time. You can see here that there are a number of takeaways, but the most important ones is, performance is already oscillating quite a bit, showing that daily patterns are already very hard to capture when dealing with these types of forecasting models. But you can also see other patterns and factors that may impact the performance of the model. A simple one to identify is the one occurring in March 2022. As you well remember, that's when we got stuck at home due to COVID. But even when COVID is not the cause of the drift, you can see that, for example, towards the tail end of the model performance, we have a new spike not caused by any lockdown or anything similar. So these problems occur very quantifiably over time. One simple thing you might say is like, your model is broken. What about other types of models? Do you want to use neural networks like LSTMs to solve the issue? Well, technically we observed similar patterns and similar concept drift occurrences over time, and the red line is the LSTM model that we developed, which was performing even worse as the other one. So we're not achieving any better performance. And we actually ran a lot of tests. We trained a lot of models across different family of models, different training set sizes, changing how much data we were using as training for our models, changing what target KPIs we were exploring. Nothing. Concept drift was persistent, always present, and it was not possible even to solve it by simply periodically retraining our models. Why so? Because depending on the period that we use to retrain these models, we might get like more or less effective performance. But the best performing ones were simply the ones that were retrained every week. And this type of constant retraining might be very costly for an operator that has to perform these model trainings at scale over an entire nation. So we asked ourselves the question, can we do better? And this is where our architecture, our framework called LEAF comes into play. I try to capture the fundamental intuition of how the LEAF framework works in a single slide. So on the x-axis, you have the various data points that might occur for the downlink volume feature that I described before. On the y-axis, we have the error of the model when inferring data input entry where the data link, the downlink volume feature occurs at that value. So here on the in the figure, we see the blue line, which is what happens when we try to forecast, infer this value using inputs that are already present in the training set. I know that fundamentally this is wrong, but it's just to give you an example. And the idea is that independently of the value of the downlink volume input feature that we're using, the error we're going to get is fairly evenly distributed independently of it. What happens if we try to run the forecasting over a set of the data that we had in our dataset that does not belong to the training? Well, we're going to observe two things. The first one is that certain parts of this distribution are actually still very low. Like the error that we get is still fairly low. On the other hand, there are portions of these distributions that observe much higher errors, and that's because we identified regions that are undertrained in the model. That the model is not as well equipped to infer forecasting for. And this is what we call the local error approximation and what constitutes LEA or LEAF when put in the framework. And that's the fundamental idea behind the LEAF framework. We use errors from the past to determine whether drift is occurring. We use simple k-swing-like methods to detect when drift is occurring. But then we use LEA to explain the regions of the data that are causing this drift to occur and use them as input to mitigate the drift problem and add resampled data to compensate for the missing the areas that are under-trained in the dataset. We apply this to our dataset, compare against different state-of-the-art techniques, going from naive retraining, so periodically retraining every 30 days, or trigger retraining, meaning that we only apply the first and the first step of the pipeline, detecting when drift is occurring, but then we just retrain with a given amount of data. And we've shown that independently of the KPI and also independently of the model, but I don't have it in here in the presentation, we improve the performance of the forecasts that we are performing. And even in the cases like the call drop rate, which is one of the KPIs that we had, where our forecasting model achieves worse performance, we still approximate the same performance, but reducing by half the number of retrainings necessary. Okay, I have 5 minutes to conclude. So where we go now? Where is my research going from this point onward? Well, there are two directions that I've identified as goals for tackling in the next few years. The first one is what happens when we translate the problems that I described today when we deploy machine learning at network scale. What does it mean, network scale? Well, this is the figure I've used a lot during my talk. One single link, one single measurement system. The reality is that obviously networks are much larger ecosystems where traffic is traversing different links. More importantly, a lot of traffic is traversing this link, very different flows, very different applications, and so on. So how can our ML-based measurement systems react given large quantities of data that have to be processed? And the other problem is, in fact, the fact that traffic spans large geographical areas, meaning that our measurement systems have to be able to capture patterns at a large geographical scale. And the question I'm asking is, like, how can we tackle these true scale challenges and still apply machine learning to solve them? I've identified 3 sub-directions. The first one being able to dynamically select a model depending on the traffic conditions that are experienced. So with changing amounts of traffic, the changing amounts of load, we can select different models that might have different cost to accuracy trade-offs in the examples I've shown before. Another example is applying data sampling, but in a different way than the one that I've mentioned before. In particular, being able to choose the flows that are going to give us the most information to maximize the amount of information that we can extract from our networks. This falls down to something that could be categorized as an admission problem to our system, to our measurement system. And we've already shown in some recent work that these types of problems can actually be approximated almost optimally using techniques like deep performance learning, even though we apply it to a different context, but it would be interesting to see how well it works here. And the last problem is trying to do data aggregation at network scale. We have shown in a paper recently accepted that we can indeed use data samples, sparse data samples across a set of measurements, non-uniformly distributed, available in a network. In particular, in the context of this research, these samples were speed test measurements, so that's why they are non-uniform, because they are dependent on the folks that are running this experiment. But we have built a pipeline to recreate geographical representations of network performance starting from these samples. And ideally, it would be interesting to see how well these techniques or similar solutions could be applied to machine learning outputs and our ability to explore the flows that are traversed. Otherwise, the other macro direction that I want to explore is the role of generative AI models in the context of networking. I didn't have time, but we've already started some work into looking at how we can use these generative models to compensate for the lack of available data. In our research, the diffusion paper that was mentioned before, we use diffusion models, which are image-based models, to augment traffic datasets used as input to machine learning models, networking-based, obviously. And we want to further explore, because these models, this solution that we created still has limitations. Like, for example, we only can create one flow at a time, and we're not able to create video sessions like the use case that I mentioned before. And the second use case where generative AI might become useful is in make the outputs of the model actionable, meaning that it could help to create a autonomous pipeline that uses the outputs of the model, like the video quality inference outputs that I mentioned before, as input to a generative AI model that is going to generate configurations that are going to then be used for improving the network configuration. And with that, I'm going to conclude. If there are 2 takeaways I can give you from this whole talk, is that applying machine learning to networking is hard. Networks are present a unique set of problems. They need to adapt to the machine learning models that we developed and the systems that use them in the real world. And in our research, we explored a number of solutions to compensate for the challenges, to tackle the challenges that arise when deploying machine learning in operational networks. And in the future, I'm going to try to tackle this problem when applied at network scale and investigate the role of generative AI. Thanks a lot, and I'm happy to take questions.
Thank you, Francesco. So I realize that